Alright, hello and welcome back. My name is Cameron Kirk and this is video number 9 in my series of videos on the DE10-Nano projects. And in today's video we're going to be doing a walkthrough, and this is an exciting walkthrough because we are going to be doing this my first SoC simple hardware adder on this Zangman DE10-Nano repository. Now I've already gone ahead and done this one on my own. And it is actually really straightforward to get this up and running. And we're going to go ahead and get this done right now today. And what we're going to be doing in this project is we're going to be implementing a very basic full adder on the FPGA, just like you would with any of our other Verilog designs in my Verilog development series of videos, which after completing this tutorial, I plan on expanding on that series with even more cool things you can make in Verilog on the FPGA, because what this project will teach you is how you can write a C++ or C software program that will run on your board, and it will let you interface with your FPGA design. So we can do things like make an ALU or make some sort of custom logic running on the FPGA, and we can control it and view the output from Linux or Debian Linux, and from our C++ program we can print out nice formatted outputs that are coming out of our FPGA design. Okay, so with all that said, link is in the description for this repository, specifically this introduction page, and if you'd like to take a try on your own, feel free to pause the video, come back later. But with all of that said, let's just dive right in. I don't think this will be a very long video. So we're going to be using the golden reference design. Let me get out of the way. We're going to be using the golden reference design for this one, of course. And one of the things this guide does is it walks you through all these things to basically gut out the golden reference design so that it's basically at the bare bones essential. And then at the very bottom it says, why are we doing this? Strictly speaking, you don't need to do all these edits, but it helps. So when I did this on my own, I skipped gutting everything out. All it says is like it makes it easier to understand, and your compile times are going to go faster. But since I'm pausing the recording, I really don't think it makes much of a difference for the purposes of our YouTube video. And on top of that, I think it makes more sense to keep everything in there and customize the golden reference design image instead of gutting everything out for learning purposes. So with that said, it is up to you if you want to complete this first initial setup guide. But what I am going to do is I'm going to set up our project folders. So I'm going to come in here under our DE10-Nano folder, and I have this simple hardware adder. I'm going to make a new folder. I'm going to call it simple hardware adder live. And then we need to get our golden reference design. So I have the downloaded CD that we've gotten in previous videos. The link is in the description if you haven't gotten this CD. Oh, and I believe this page tells you how to download it. Download the CD-ROM. Yeah, it's got it right here. I'm not going to put the link in the description. But anyways, we'll quickly go back. So here is the golden hardware reference design. We're going to copy this, and we're going to go back into my newly created simple hardware adder live and paste it in here. And we're also going to go to the next page. And we need to have a simple adder implemented, and this looks a lot like what we've seen in one of my Verilog videos, but this is a 64-bit adder, which takes 2 inputs and has 1 output and adds them together in parallel. So we're going to create this IP and put the code in there. So I am in my simple hardware adder live folder, and we're going to go into IP, and we're going to make a new folder, and we're going to call it simple adder. And I'm going to open that up with code. And we're going to make a new file. We're going to call it simpleadder.sv. Enter. We're going to grab that code, copy. Oh, it's going slow. Paste it in there and save it with Control S. Okay, I'm going to close this down, and this is good to go. So now we're going to skip the primer on Avalon memory mapping. Feel free to read through this if you like. Some helpful background information in here, but we're just going to jump right in with getting this working. So then they're talking about the IP catalog, and basically they're highlighting this parallel input-output until FPGA. So basically we're going to jump into QSys, and we are going to add 3 of these parallel I/O, 2 for our input and 1 for our output into the FPGA and from the FPGA. And this is basically how you can set up a some memory that is going to be for some sort of parallel input or output. Okay, pretty self-explanatory. Now, one of the things they do is they create a they create a their own custom parallel input-output. I don't think it's completely necessary to do this, but I followed along with what they were showing, so we'll go ahead and do that. We're going to make a new IP folder, we're going to make a new folder in our IP folder. We're going to call it PIO64, and we're going to open this with code. And we are going to do PIO64out.sv. And we're going to copy this, paste it in there and save it, and then we're going to make one called PIO64in.sv. And we're going to go down to this one, paste it in there and save it. Okay, so with that all done, we're going to fire up our Quartus. We're going to open our QPF file for our Golden Hardware reference design. Oops, it opened on my second screen here. Give me just one moment. Okay, I'm going to pause the recording until it starts responding again. Okay, I finally finished opening. We're going to click on Launch IP Upgrade Tool and then click Perform Automatic Upgrade. And one of these might fail, but that is okay. That will be expected. Okay, I'm going to pause the recording and we'll come back when this completes. Okay, we are back, and like I said, don't worry about that failure. Everything is okay. Let's go ahead and jump into QSys, or Platform Designer. You go to Tools and QSys. Go ahead and open up your SoC system.qsys. And I don't think this will take too long, but I'm gonna it's gonna perform an automatic upgrade. I'm gonna pause the recording while this loads. Okay, so that loaded. I'm gonna click close on this. Everything looks good. Click close on that, and I'm gonna go full screen on this. We're going to go to File, New Component, and what are we naming this component? PIO64out. parallel IO 64. Bit output. Okay. Click on Files, add a file, IP, PIO64, PIO64 out. Analyze. Looks good. Signals and interfaces. Change this to PIO64 out. Type to conduit. Associated reset to reset. Click on this one and type export. Looks good. Now we'll click on S0 and give it a reset. And then we'll click save, or we'll do Control S to save, and then we'll do finish. Now we need to make another one for the in. Everything should be the same except for changing out to in. PIO64 in. Parallel IO 64-bit input. Oh, man. Get that back. Whoops. IP PIO64 in. Analyze. Good. Close. We'll go to signals and interfaces. This is going to be changed to basically the same steps. 64 in with a reset and with a conduit. This is going to be let me make sure I'm not making a big mistake here. S0 gets a reset. And they did change that to export. Everything looks good. So we'll do a Control S and we'll do a finish. So now we're going to wire the components. And we're going to have two inputs, one output, and then they want us to have this bridge, but we're not going to add in this bridge because in the guide they had you remove it, but we actually have it right here, the MM bridge, pipeline bridge. So like I said, there wasn't much of a point to gutting everything out because they kind of put some of it back in. So theirs looks like this. We're not going to add the bridge, but we will edit the bridge and change the data width to 64 and click finish. So now it looks like that, and we have the same thing. Reset clock and S0 is AXI master. So here is AXI master, I'm going to minimize a couple of these. Oh, okay, so we don't want to use, let's see here. We want to use the heavyweight, so not the lightweight, but the heavyweight. So H2F AXI master is what we want to be connected to. So we're not going to be connected to the HPS0 H2F lightweight AXI master. We're going to uncheck that. And what we want is the H2F underscore AXI master. That's the heavyweight bridge. So I just made that little change, and now we're using the heavyweight bridge. So we've got all those changes. So now we're going to double click the output component we've created, and it'll just add it in at the bottom. And we want two of them. So output, oops, we just click finish, and then we get another output, and we click finish. So now we have two of these. I'm going to minimize some of these other I/O components so that we can see things better. Minimize the clock. Okay. Things are looking good. First step is to export our conduit signals. So they do adder A, adder B on the PIO conduit. So this will be adder A, and this will be adder B. Okay. Now we need to connect it up, and S0 should be connected to the master M0 on the bridge. So we want M0 going to S0 for both of them. So here is S0 and connected to M0. So when I hover over it, it tells me what this node will connect what to. So the start is mm_bridge_0.m0, and the end is PIO64.1.s0. So we'll click that, and then same thing for this first one. So now they're both connected. Don't worry about the error messages. These guys will deal with it. And then we need clock reset for both of them. So clock. What am I missing? There we go. Okay, so maybe we want all these expanded. I'm going to expand these all back. And I'll expand these as well. Okay. All right, so clock gets clock, reset gets reset, and reset gets reset, and clock gets clock. Cool. Easy peasy. So now we just have this error right here. So now we need to get an input, and we're going to export it as adder sum. So here is our input. So we'll double click our input. There it is. We'll click finish, and it gets a clock and a reset, and then S0 also connects to the same spot, M0, and then we're going to export adder sum. Okay, and I think that is everything, so let's keep going. Okay, here's some information about memory mapping. We're gonna just scroll through this. So they're pointing out this is the base address and this is the end address, and then we need to change our base addresses for our three components because right now they're all just kind of stacked on top of each other. So what we can do is we can make this one start at 8, right? Because this one starts at 0 and ends at after 7. And then, so this should pick up at the very next one, 8, and it'll end at F, which I believe is automatically calculated. And so since we're ending at F, then when we add 1 to F, we move over a place, a hexadecimal place, and then it automatically has the correct endpoint. And that's what these changes are saying. It's also pointing out that if you were to right-click and edit on our bridge, so we can go ahead and do that now, that with this box checked, it has 18 for the address width. And that is determining how big our bridge is right here. So this value right here is determined by that. And you could change it to be something manual if you want to. But keep it as automatically determined. So this is just explaining that. Okay, so we're going to save it. Control S. Close that. And then generate HDL. And click generate. And I am going to pause the recording here while this loads. This will take a few minutes. Okay, that is all done. We can ignore those warnings. We're going to click close and click finish. Okay, so click finish, and now we're done wiring. Now we're going to do the simple adder. So if we switch over to files, oh, where are we? Oh yeah, this takes a second to recover, so I'm going to pause the recording until it catches up. Okay, we're back, and this little window popped up, so we'll click OK on that. And we're going to... Oh, come on. So slow. Alright, I'm going to pause the recording. Okay, finally caught up. We're going to click on Files, and then we're going to expand this one down. I forget what we're doing. I think we're adding a file, right? So right-click up here, and then click Add Remove Files. Woof! It's going really slow. I'm going to pause the recording and restart Quartus. Give me 1 second here. Okay, we're back, and hopefully everything is under control now. We're going to go to Files, and we're going to add and remove a file. And what we are going to add in here is our simple adder IP. So we go to our IP, there's our simple adder. We're going to open that. Oh, I clicked on the 3 dots right here to add another file. We're going to click on Apply, and we're going to click on OK. Man, what is my computer doing? There it goes, it caught up. Now we're going to click OK. Sorry about that, I don't know what the problem is. Okay. So now we're going to go into this Verilog folder, or this Verilog file. Let's go back to Quartus. Under here and under here, and we can see that we have our output wires here, which is looking good. These are all of our exports from the conduit. This is all generated Verilog code, but what we need to do is actually wire it up to the simple adder. So it's just sort of saying check those out, they're there, and then we're going to do this. Oh, we need to add both of these things. So we're going to go to the hierarchy, we're going to open the top level entity, and we're going to go down to here, and I'm just going to copy these 3, paste them underneath. Here is 63, 63, 63. So bit 63 down to bit 0, including 0 is a total of 64 bits. And we're going to have adder A export. Let's see, can I get them right here? Yes, I can. Adder A export, adder B export, and adder sum export. all those wires. And then we're going to do an instantiation of our simple adder module. So if we look, well, it's all right. We're not going to take the time to do that. Just right under here. Simple adder, my adder, semicolon. Don't forget the semicolon. And then we're going to push enter. And we're going to have .a. And then we need this guy right here, comma. We're going to do B, and sum gets connected to sum. Just like that, and then take this comma off. We'll save that. And, oh yeah, I already... Oh, and then inside of our SoC system, yeah, right here, we need to add a comment for adder, and then dot adder underscore a underscore export adder a export, comma, and then dot. You get the idea. Let me just focus on typing this out. All right, let me just double check if I'm missing anything. I don't think I am. I think we got it all. Yeah, this is the same screenshot as this one. Okay. And there's the completed source code. We're going to skip that. Okay, we're going to compile the design. So it's telling us we can double-click the assembler on the left side menu to complete. So I double-click this guy. I think when I do that, it crashes for me. I think it's because I'm on version 17 of Quartus. I'm just going to click this blue play button. I'll say yes to the save to the changes. And I'm going to pause the recording, and we will come back when this is all done. Okay, we are back, and that is done. So the next thing we need to do, and if you haven't done this already, I do already have a tutorial on how to set this up, but we need to jump over to the DE10-Nano board now, and I have the USB cable plugged into the UART to USB port. Ethernet is connected, and I am about to plug in power. Before we do that, though, let's go ahead and open up PuTTY. Switch over to serial, baud rate 115200, COM port 3, and click open, and go ahead and plug in power. We need to make sure that our FPGA bridges are online and enabled. I have a video on how to do this called it's another walkthrough. I'll put the link up in the top left corner up there. But basically we're going to flash the design tree with a new device. Did I say design tree? A new device tree that has all of our FPGA bridges enabled. Alright. So I just logged in here, and I'm going to change this screen size. Appearance, size 14. Apply. Okay, let's just go ahead and run this command, And they are all enabled for me. Very good. And there's a link here for how to enable those. Okay, so now we can flash our design onto the FPGA. All we need to do this is we go back to Quartus, we go to File, we go to Convert Programming Files, we change it to raw binary file. I'm going to change it to Simple Adder Live RBF. Select SOF data, click Add File, go to Output Files and select this SOF, click Open, and click Generate. Should not take long at all. While that is generating, I now have a FPGA binaries folder. FPGA binaries folder directory. Okay, let me minimize this, click OK on that, and click Close. Okay, so what that just created for us is inside of our project folder, we now have a Simple Adder Live RBF. If I hold down Shift and right click, I can open a PowerShell window here. And I need an IP address, so if you don't know how to get that, it is ifconfig. And here is our IP address. I'm going to SCP our Simple Adder Live RBF. I hit tab to autocomplete typing that for me. We're going to send that to the user roots at 192.168.0.62 : and this is going into the home folder / FPGA-binaries. Is that what it is? FPGA-binaries / enter. And authenticate, and off it goes. So now when I come in here and I do an ls on FPGA binaries, we now have this Simple Adder Live. Now if you set up U-boot and you set up basically our SD card image for the DE10-Nano using our setup, I have a video on that as well if you want to go check that out, and there is a walkthrough on that. Let me see here. There is a guide on how to do this, but I will show you right here and right now. So in my home folder, I have this FAT folder, and we're going to use that as a mount point for /dev/mmcp1 mounted to FAT, enter. So now when we ls the FAT folder, there's all this stuff in here. And this RBF here, whatever RBF that is named with this name, that sits in this directory at this mount point, that is what is going to be used to flash the FPGA. So all we need to do is issue a CP from FPGA binaries, the Simple Adder Live RBF. We're going to send that to the FAT folder for SoC system RBF. We're going to overwrite that with a copy. Push enter, and then we're going to do reboot. What is it, reboot now? Or just reboot? Okay, and that's going to start rebooting. And as soon as it reboots, it is going to flash our FPGA with our newly created golden reference design image with all of our Simple Adder hardware added into it. One other thing I do think is worth mentioning is if you followed along in our previous video where we wrote our simple Linux driver, let me just sign in here. I would recommend you go ahead and put your backup, sorry about that, put your backup device tree back on as, sorry, let me get that mount point again before I continue talking. Sorry, I forgot to put the target folder. Okay. Your backup, your device tree binary backup. Just issue a CP SoC FPGA cyclone Oh, I see what the problem is. Inside the FAT folder, SoC FPGA underscore backup. We're going to send that to the FAT folder and overwrite the SoC FPGA dot device tree binary. Go ahead and issue that, and actually I will do that now just to make sure, and do another reboot. So this is taking off our device tree entry that has the custom LEDs on it, just in case if that is going to interfere with what we're doing here for this project. I'm also going to run this command one more time to make sure we have FPGA bridges enabled, because I don't know if I changed that backup or not. I think I typed the password in wrong. I did. Okay, there we go. And issued this command, and everything is enabled. Perfect. So we have our blinking LED. Let's go to the tabletop. Blinking LED, good to go. I'm not sure why all the other LEDs lit up on this one, but I'm not going to be too worried about it. We'll just keep moving along. That did that to me when I did this on my own before this recording, and it didn't seem to be a problem. So now we are ready to write the software, and I am going to compile my software using our Ubuntu cross compiler over here. Oops, you cannot see my screen. Go back over here. Okay, so we're writing this. We're writing the code, and I'm going to compile this. I just went to the next page. I'm going to compile this using my cross compiler, and in order to get that cross compiler working, we need a export command. There it is. We need this export command. So it's on the screen now if you want to type it out. I will also add it in to the link description, or the video description. Well, let me just make a note of that so I will remember. Okay, that is one thing you're going to need. Push enter. There it goes. Okay, so if I go into our DE10-Nano working directory, you can see I have here a directory called simple adder, and what I'm going to do is I'm going to make dir simple adder live, and then I'm going to code simple adder live, which will open Visual Studio Code. Okay, while that is opening, we're going to create a program called myprogc. I'm going to copy that name, and we're going to make a new file, paste in the name, and here we go. Okay, so the code does a good job of breaking down how some of this works, but let's just go all the way to the bottom. And not the C++ program, we're going to get the C program. We'll get the full program code, paste it in here, and save it. And in the next video I'm going to do, I want to talk about a better way of writing this code so that it's a little bit more simple and a lot less complex, but we'll save that for the next video. For now, feel free to look over this code if you like. Basically, I can talk through this quickly. We're getting some variables to hold our values. We're getting some pointers to point to memory locations that control the registers of our FPGA IP, so the adder. So this is a pointer to the location where we put in the values into the FPGA. And these are variables in our user program. And then we have a pointer to a bridge map. We use a file descriptor to open up this mmap call, and we use these offsets from the bridge map to point to the correct locations, and then we use pointer dereferencing to assign values A and B, and then check what the sum is. And that all happens combinationally. So as soon as these signals are applied, the result appears over here, which is very, very, very fast, very high performance. And then we close out. That's the basic idea of what's going on with this code here. Okay, so I'm going to close out of Visual Studio Code. We are now ready to build our design. So we're going to cross-compile this. I'm going to copy this command and paste it in here, push enter. And oh, I didn't go inside my simple adder live ls. And I am going to mv myprog.c to myprog.live.c, enter. And then I'm just doing this for the sake of consistency. We're going to make myprog.live.c. Okay, push enter. And that should have worked. And now we have this executable program here. And we need to SCP it over to our board. So I am going to SCP myprog live to root at 192.168.0.62 : for the home folder. Push enter, type in the password, and off it goes. And now back over on the DE10-Nano, we can see that we now have a myprog live. And if we run myprog live, it wants two numbers. So we'll do 100. Oh yeah, 110 plus 200 is 310. So it works. That is pretty much it for this video. And keep in mind, this is a this is a 64-bit full adder that's implemented in the FPGA. So as soon as we write values, we get that continuous assignment from Verilog. As soon as one of the operands change, so maybe we can write to these operands individually. But as soon as these values are written, the results immediately shows up in the results memory location, and it is that fast because it's a combinational circuit. The full adder is adding these values in parallel. Right? In parallel? Yeah, you just have to wait for the carry to propagate through the full adder. But you can put really big numbers in here, and it will still work. I don't know if we had some concatenation there. I may have went too big. But yeah, you get the idea. So I hope you enjoyed this one. I will see you in the next video where I just wanted to sort of give some tips on making that code a lot simpler. Like, for example, one of the things they're doing here is they're actually making individual pointers to these memory locations and tracking them all individually. There is a much better way of doing that, especially when you configure it, and especially when we have the control to, I guess we have QSys closed, or System Designer. You have the control to set memory locations contiguously or uninterrupted back to back to back. Yeah, there's some good techniques I can show you for that. Anyways, I hope you enjoyed this one. I'm very excited about what's going to come next. This is a huge project for us to do, and it's going to open up lots of other projects to come back with on the Verilog development series. Can do some very cool stuff this year. Anyways, thank you for watching, and I will see you in the next one. Take care. Bye-bye.